Hello and welcome to What, So What, Now What. If you missed our previous episode, you'll have missed a brief update about the new format we're going to be approaching this podcast with this year. And so today is actually a bit. It's going to be about hyper, and I'm joined by my co-host Ravi.
Hello, hello. How are you doing?
I'm good. How's your new year?
New Year was good. I'm slowly getting back into the swing of things. So it's a nice, easy way back in. After a bit of the chaotic Christmas period. So we're going to be talking about hyper.
Absolutely, we're going to be talking about hyper. I'm really excited about this because this technology has actually been around for a while, and definitely in the Tableau sphere, it's definitely something that we've all started using, and I've almost forgotten sort of when it was introduced and how it was introduced. So we just wanted to take a deep dive into the technology and just
Mhm.
highlight why it matters.
Yeah, for sure. So it's interesting. So hyper was dropped in Tableau 10.5, right?
Yeah.
It was an acquisition. So I think they bought it in around Easter time
Hmm.
2016. I think it was March. And it's basically a technology that was developed in Munich by a couple of Germans, um, and it's basically an academic endeavor. There was a project or something that they worked on,
Hmm.
and they were looking for a bit more financial backing, and Tableau came in and purchased them because I think Tableau also wanted to move on from the TDE. So taking a quick step back, so what these two technologies, TDE and Hyper, these two file types are, they're extracts of data. So what you're doing when you connect to a database on Tableau or even an Excel spreadsheet, you have the ability to extract that data into what was formerly a Tableau data extract or what's now a Hyper extract. And when it was demoed, I think the first time it was demoed was in Austin, 2016. The biggest excitement was the speed increase
Yeah.
and the speed of processing it brought, and the fact that you can query millions and millions of records of data on the fly, and it's so much faster to extract, and the processing is so much better. But I think when we dug a bit deeper into this, we found out there's a lot more going on. Than just what we see, which is like like I mentioned in the previous podcast, I'm very much I just need to know what it is, and so I can
Hmm.
explain it. Have that
Hmm.
have that one liner that you mention, so you don't sound stupid. Um, and for me, it was like, oh yeah, it's just a lot faster. Its processes and extract a lot quicker. But I've never really ended up digging into like, okay, but what is it? Like, is it a database? Is it an extract? Like, how does that actually all that work? So that's what Hyper is. How have you found digging a bit deeper into Hyper, Tim?
Yeah, it's an interesting one because speed is often the thing that everyone talks about, and I think after that you just kind of put the technology to bed, and I think that's actually a mistake. Um, Hyper is a lot more than just about speed, and to sort of dig into it, you have to kind of go back to its founding principles, and it was actually derived from an academic background, and essentially it was spun off by two Germans who were trying to understand why today's databases were so slow and had so many trade-offs compared to some of the hardware and technologies that we have available to us today. And
Hmm.
so the core principles were very, very simple. They both wanted to build one system. This meant that you only needed to have one database that could serve the purposes of being transactional, or an analytical database, or sort of beyond relational kind of infrastructures as well. They wanted it to have it in one state so that you didn't need to have, for example, with the TDE, when you add data to it, you can't extract the data and be reading data from it at the same time. So they wanted it to be able to be accessible in multiple states. And then
Hmm.
the other sides of it, they wanted no trade-offs. Yeah. Given those requirements, and they wanted no delays. So speed is actually only one of the four key factors that they wanted to sort of implement into this. And I think as we dig into this, I must stress we're going to be talking about concepts that are actually, unless you dig into the research papers and you understand a lot of the terms around them, we're going to be massively simplifying some of these concepts
Yeah.
just so that we can, so we can A, have a discussion that you and me can keep up with, but also B, relay them back to you in a way that kind of makes sense. So we're going to be using a lot of analogies and metaphors and oversimplification of a lot of concepts. But we just want to stress that up front before we go into it.
Sure, and I think it's also worth stressing that neither me nor Tim have a hard background in commuting in terms of academia. I'm an economist, and Tim, what did you study again?
I'm generalist, management.
Right, exactly. So like this sort of top level view is really um, really useful for us as well. So it's breaking down these concepts so we understand them, and then
Hmm.
also you, our listeners, can understand them a bit better as well. I think what you mentioned there about computational power is really quite interesting because it's that sort of the rate of innovation is so much faster in the last 10 years even versus the previous decade, right?
Hmm.
I think the tweet going around very a lot is that 1999 was now 20 years ago.
Yeah,
Um, so
yeah.
you know
It's crazy,
with
isn't it?
it's yeah, exactly, and the leaps and bounds that we've gone through in what we do and how we access content and information has changed so much. But fundamentally, the computer power that generates this, that makes all of these things possible, you know, the fact that I can play Fortnite on my phone is possible because the Apollo 11 computer that landed on the moon had like 1,000 times less power than like the iPhone 5.
Yeah, yeah.
Like it's we've condensed so much technology into smaller things, but it's the question of have the wider enterprise level of technology is kept up, and I'd argue no, based on what we found.
Yeah, absolutely, and so we're kind of gently moving into the so what era here,
Hmm.
and so to summarize, Hyper is, as Tableau terms it, a next gen database system, right? It's not a database that you can buy off the shelf today. Tableau definitely haven't yet spun it off as a database, but it's the driving engine behind Tableau Server, Tableau Desktop, and pretty much most of the new kind of innovations from Tableau. And so if we do take that step back and start to think of the so what, Ravi, you touched on the computing
Yeah.
landscape, and I think it's important to take that step back and just sort of, you know, touch on a couple of points regarding hardware and hardware capabilities of today versus 20 years ago. And so the simplest thing you can look at is hard drives. I mean, I remember buying a hard drive, one of those USB pen drives, and the most you could get on it was 4 MB, and that was revolutionary because the floppy disk I used to have could only contain 500 kilobytes, right?
That's what, three songs?
Yeah, exactly. And now, like, just to download one Instagram photo, it requires more than just 500 kilobytes or whatever you could fit on a floppy disk. And
Hmm.
so the cost of computing has come down massively. And hard drives is one aspect, but the other aspect that people don't often talk about is memory. And by memory, I don't mean memory in your hard drive. I'm talking about random access memory. So this is the kind of memory that your computer uses to store information whilst it processes it. Yeah.
Yeah. So short-term information, right?
Exactly, exactly. And this is kind of how computers were built. They were built with this sort of logic in mind. And so the way a typical computer works is you have information stored on your hard drive, and your computer needs to process something. It takes some of that information, and whilst it's processing it, it leaves it on the memory so that if you need that information again, it can pick it up and process it or carry on processing it. So if you do something like Photoshop editing, that is a mostly in-memory process because it has to keep all that information in memory so you
Hmm.
can keep on editing your image. And if you look at the price of memory, from 1994 to pretty much where we are today, it's gone from costing roughly $45,000 for a megabyte down to being under $2, to the point where today you can buy a 1 terabyte RAM system for about $15,000, which sounds like a lot of money, but for 1 terabyte of random access memory, that's just revolutionary. And so it brings a lot of sort of capabilities into scope. Um, the other aspect, obviously, is also that the computer, the thing that processes that information, that has also been progressing forward. So, back in the day, you used to have single core computers. I remember some sort of revolution when you could start having dual core CPUs, and everything just got insanely faster. And ever since then, what you've seen in computing is Moore's law is starting to slow down because we're reaching the theoretical limit of what's possible in terms of physical architecture today. So
So Tim,
essentially,
what is Moore's law?
so Moore's law is a simple law that this guy called Morse came up with, and it basically suggests that every 2 years, the number of transistors that you can fit in a given space doubles. Okay, and so
Hmm.
back in the day, 1970, that number was about 1,000, and where we are today is that number is about 20 million. And it's actually getting harder and harder to squeeze more transistors into that space. It's actually peaking off, so it's no longer this exponential effect that you'd see on a graph if you use the logarithmic scale.
Yeah. So what's interesting about that, what you mentioned there was like, I remember I was very young at the time, but I remember when the dual core processor came out, I was like, it's a dual core processor. You see the adverts saying like,
Yeah,
it's dual core, I can fit two into this. And
yeah,
now we're at like quad core and no one bats an eyelid, right? Like
yeah,
it's like, oh yeah,
yeah.
of course it's quad core. What else would it be?
In fact, it's almost seen as the number of cores going up is almost now seen as a almost lesser technological advancement compared to being able to produce your circuitry at a smaller level. So you'll often hear
Right,
in
exactly.
IT
Real
terms,
estate.
yeah, real estate. So the difference between a 14 nanometer circuitry and 7 nanometer circuitry. So it's literally exactly as it sounds. The circuitry is much, much smaller on a 7 nanometer process compared to a 14 nanometer. And so what that allows you to do is use less power because you don't have as much circuitry to run power through. And that means you also have less resistance, all this, wonderful physics stuff. But it
Mhm.
also means you can fit more powerful units into a smaller amount of space. And that is what's more important for things like phones and computers and laptops. It means cooling is easier. It means you can sort of get advantages from being able to do things in sort of interesting ways. And so things even like neural networks and sort of AI architecture is easier to do because you can fit them in smaller and smaller spaces.
Yeah, and just a point on nanometers, it's like a strand of DNA is 2.5 nanometers in diameter.
Yeah.
So
So we're getting really, really small. And also
exactly.
there's also like just big there's differences in the different types of 7 nanometer processors you can get. So for example, Intel's version of 7 nanometer isn't the same as Qualcomm's version of seven
Oh,
nanometers
really?
it's yeah, it's not like an industry standard. It's simply the name for a process, but it actually, when you get into the nitty gritties, each sort of supply or fabrication chip fabrication company will have slightly different ways of getting those benefits. Even it going into like things like 3D architectures, which is just way beyond this podcast. But yeah,
Right.
so we're kind of getting sidetracked there. But if we go back to the overarching story here, the simple fact is that computers are getting faster and more capable. The hardware has changed massively since 20 years ago,
Hmm.
but many of the databases, many of the principles we rely on are much older than 20 years ago. And so if we drill into, why is hyper so revolutionary, we can actually start to address some of these concepts right from the top. And so let's maybe just go through some of those. There's really three or four key concepts here of why hyper is fast, unlike its competitors. And I'll say competitors in this sense because if you're going to compare it to other databases, you have to view other databases as competitors, even though it's actually not a product. And so the first one is query optimization. Now, query optimization is something I think we're all familiar with Tableau. When you're writing a query or when you're building a Tableau workbook, one of the things you might do is look at the way that Tableau is building the query.
Hmm.
And you might find areas which aren't optimized. And so what you might do is change the way the chart is built so those queries are optimized, or you might change the way the database behaves so that that query is optimized. And
Exactly.
better optimized queries means they're basically asking for just the right amount of data in the right way so that you can then work with it in your visualization or in your database.
It's basically building, saying something in the most efficient manner, right? I think
Yeah,
is the best way to
exactly.
put it. Because
Exactly.
once we start talking about queries, I always think of translation analogies is the easiest way to understand these sorts of things.
Yeah.
And in this sort of thing, you're basically saying that if it's when you start learning German, for example, and you're saying, can you point me to the left-hand directions to the pub or something like that in a
Yeah.
long-winded way. But then when you start learning a bit more and optimizing your language,
Hmm.
you're more likely to speak in colloquialism, saying, "Where's the pub?" sort of thing.
Exactly. And so you kind of hit the nail on the head there. The way you get better at query optimization is to surround yourself with people who are good at that kind of language, right?
Right.
And it's it's the kind of thing in database and even just in general in terms of research. It's very hard to yield results, and so there are not many researchers that actually are good at this because it's just simply the kind of thing that takes so long. And even let's say you spent 5 years researching a certain type of query optimization, it might not actually yield any results that are beneficial in today's sort of enterprise context.
Hmm.
And so when Tableau acquired Hyper, it just so happened that one of the leading sort of thoughts on query optimization happened to also be on the Hyper project, and that was Dr. Thomas Neumann. And so, in many ways, that was something that Tableau very lucky with. But we should also highlight that Tableau's own team have actually been, from the top, very, very upfront about improving the way that queries are done and
Correct.
making sure that queries are always optimized. So I'd say this is a small point, but it adds sort of a weight to Tableau's sort of research and push to make better optimized queries for a whole range of databases that Tableau sort of interacts with.
Exactly. I think this is the thing that Tableau seems to do very, very well in terms of they'll push their own boundaries as far as they can go, and then they'll
Mm-hmm.
appreciate the fact that they need to bring in some external influences to help develop the product further. So, for example, Hyper was one, and then we had the natural language processing company that was bought
Yeah.
a couple of years ago now, or last year.
Mm-hmm.
Um, just to help push that thinking process further and move that needle along to keep up with the market and the changing world we live in. And also another thing to touch on is Tableau's research team in general. If you go on research.tableau.com, you'll find that a lot of the prominent thinkers in the space we work in data and data visualization and mapping and now databases and optimizations. Tableau has a lot of that the leading thinkers in those fields. Like I'm thinking Maureen Stone on color theory. You've got Robert Corsara on storytelling, Sarah Battersby on mapping. So it's very much something that's on
Yeah.
Tableau's mind in terms of innovation.
It's part of the DNA of how they work. They're very
Right.
research driven, and they put as much effort into research as they do into building their product, which is what makes their product better. It's research driven and innovation driven.
Hmm.
That's the point. And so that's sort of the first step, right? When you're talking to a database, you build a query, and if that query is optimized, then the database is more likely to respond faster and better, and it should also take less time because you're getting it to do exactly what you need it to do.
Right.
Now, there is actually another step between the query optimization, so writing a better SQL query, and actually getting a response back to the from the database about that query. And for this, I'm going to talk about query compilation. Okay, so when you write SQL, that is essentially code that you and me can read. In fact, in Tableau, if you record the performance of any workbook connected to a database and then you stop the recording, you'll get a view that shows you all the queries that were sent to a database and the SQL that was written to request that data. Now, when you actually fire off that SQL query, the computer can't read that. And by that, I mean the processor itself does not take your nicely sort of human readable SQL and
Hmm.
process that. What it actually does is it converts that SQL query, essentially that code and instruction you've given it, into something called machine code. And machine code is quite simply put ones and zeros. Okay.
Yeah.
I'm
I
not going
mean,
to go into more detail than that because
yeah, no, neither of us are experts on how the nooks and crannies of machine code work, but
yeah,
again, it's effectively a translation system, right? It's
exactly,
changing it
exactly.
from a language that you and me understand and cutting out the middleman of let me just quickly stage this and change it and basically saying, hey, let me help you communicate this better to the
Exactly,
computer.
exactly, exactly. So it's just ones and zeros and lots of numbers. If you saw it, you'd think, "What is this?" It looked like the Matrix. It literally looked like the Matrix. And so, if we take a step back, what the team at Hyper discovered, and it's actually there's a paper that they refer to, which was written by MonetDB, which is another database, where MonetDB essentially proved that even their hand-coded C program-based queries performed faster than a computer generated or computer compiled code. And so what I'm saying here is that when the team took a query and wrote it in machine code, essentially ones and zeros, and then they got their database to try and do the same thing, the hand-coded version was still faster than what the machine had created for itself. Which, if you think about it, is actually doesn't make sense, right?
No,
Why can't
absolutely
a
not.
computer can create machine code that it can read as fast as we can write for it, if that makes sense? And so this is what Hyper tried to answer, and it actually goes back into just how the database itself is built. And to kind of keep this short and sort of unabstruse and not abstract, what Hyper basically does is it kind of plays into this. When you send it a SQL query, it doesn't process that SQL. What it actually does is it converts that SQL into machine code. And it does that by writing something called LLVM. And LLVM is an acronym, but in summary, LLVM is the intermediate step between machine code and a programmer's code. So let's say you do HTML coding, or let's say you do SQL programming. Yeah, what you write is a conduit that then gets compiled into machine code for the computer to process. And LLVM is essentially much, much, much simpler. It's basically one step ahead of that. So if you were to send LLVM to a computer, it would then almost instantaneously convert that into machine code that it could then process straight away. So it's one level in between what a programmer writes and what a machine understands. Okay?
Exactly, and that's that translation step that I keep referring
Yeah,
back to.
exactly.
That's what it's doing effectively, right?
Yeah, exactly. And so what happens here is that because Hyper's doing this, you're actually able to get highly specialized and highly optimized queries generated for the CPU in question. Because the other thing to bear in mind here is that not every CPU is the same. Every single year, new CPUs come out. New manufacturers compile different instruction sets into their CPUs. And so being able to compile instruction sets that are specific to that CPU allows you to do optimizations for that query that only you could take advantage of in that specific processor. So when I say CPU, I mean processor. You have to keep reminding me to kind of break down
Yeah,
these acronyms.
yeah, right. And then the two like main types of processors in the market today are you've got AMD Athlon. Well, no, Athlon's the type, so AMD
Yeah,
and Intel, of course, is
Intel, AMD,
the market.
Intel. You've got another sort of split going on, which is between ARM,
Hmm.
ARM-based processors, and Intel-based processors, and all this stuff is massively in flux at the moment. And so the benefit here is that you're probably wondering, okay, so what if it can compile this faster? So what if it can get this all
What's the
done?
value, Tim? What,
What's
what,
the
what,
value?
what,
Yeah.
what am I seeing as a user of Tableau that's better?
Okay, so it essentially comes down to speed and basically how close you can get your SQL query to the computer's sort of processing. Okay, and
Hmm.
this is two pronged. So number one, it's taking less time to write the SQL query because you're optimizing it.
Yep.
Number two, you're then translating that into machine code a lot faster than it would traditionally take because you're doing it using that middle step I described called LLVM.
Hmm.
And then earlier on, we talked about memory. Okay. So memory is a really, really important thing in this game because when you're doing all that work, you need to be able to put what you're doing somewhere. So if you give me a pack of cards and you tell me to memorize the order in which they are, I need to be able to put what I memorized somewhere. And for me, that's my brain. But imagine if I had to write it down. That would take me longer to write that down. Yeah.
Hmm.
I'm assuming that my brain and my memory is better than my handwritten memory, which it isn't. But assume I had to write it down, I'd actually physically have to wait for me to see the card, write it down, make sure I've written it down correctly, go to the next card. And so you start to get a picture. This is taking time. And so in computing terms, what this relates to is essentially how far away you are from the job that is actually being done.
Yep.
And by this, I mean how far is the information that's needed away? How far away is it from the computer, the actual processing that's being done? And it's hard to sort of imagine this because in real terms, this is all happening inside of your laptop. There's no great
With almost
distance.
no
Yeah,
delay, and it's just
exactly.
happening,
Yeah.
right?
We're talking about infinitesimally small periods of time that massively scale up. And so we're just going to sort of try and give an analogy, right? So if I put a bit of information inside of my processor, inside of my computer's processor, that is the equivalent of having that information on my desk in terms of, if I'm doing something and I need it on my desk, that's just like reaching across the table and grabbing it from my desk, okay?
So that's
Now,
you getting your list of the
yeah,
cards you've memorized, right?
exactly. I've just literally picked up the list from my desk and I'm now reading it
Hmm.
straight away. Now, imagine that that list that I've written down is now no longer on my desk. Imagine it's on the bookshelf, okay? Now, that's still in the same room, so I just get up off my chair and I go to my bookshelf.
Yep.
Not so hard. Now, imagine that that list is actually next door. So I have to get up, go out the door, go next door, get it, look on the right bookshelf, pick it up, come back, sit down, read it, and then process it, okay? You're starting to get the idea here. It's taking longer and longer
It's
and
more
longer.
and more tenuous.
Exactly, more and more tenuous. Now, imagine we are where we need to be, which is RAM, so random access memory, what we talked about at the beginning of the podcast. Okay. Now, RAM is the equivalent of being in the building next door. So imagine that I'm sitting in my office and I realize I need that list of cards. What I've got to do is get up, go out, go into the lift, or call the lift, wait for it to go down, go out, go into the other building, go to reception, do whatever you need to do, get to the floor that has your list, get the list, and then do all of that to come back again. That is actually what random access memory is like, okay? And that sounds really, really slow. But wait till I explain how a hard drive actually works. You see, when your computer talks to your hard drive, in real terms, that's the equivalent of having your list on the other side of the planet, okay? So, although your hard drives and SSDs are getting ridiculously fast, in computing terms, the information is actually being stored incredibly far away. And this all gets in the way of processing data and processing information very, very quickly. And so, because Hyper does as much of its processing in memory as it possibly can, it's effectively minimizing the travel between the data and where the processing is done. So it's essentially the difference between going to the building next door and going to the other side of the planet. That's basically the best way to think of it. And so, in summary, a lot of databases today use the hard drive option. They don't store a lot of information in memory. In fact, they don't store much, if at all, information in memory. It's all read from disk. It's all read from a
Right.
hard drive.
And then if you add in the factor that a lot of these databases are behind firewalls, they have security layers and authentication options, you start to see like the fact that you're sending off a query and the fact it's taking a while to come back to you, it's all relative to all of these different things added up together. So
Yeah,
sure, it
exactly.
might be in a hard drive, but then also you have to jump over all of these different things to get to the other side of the earth in this case.
Exactly.
Before you getting your response, which is why you sort of get people's annoyance with the fact that it takes ages to query big data, as it were.
Yeah, exactly. It's funny because you will get technologies. You get companies who claim to have databases that are super fast, but what they're doing is essentially brute forcing this approach, which is they're storing all of this information in an architectural format where basically the computer knows where absolutely every single bit of data is. So it's actually cheating. It's a bit like having yes, your data might actually be next door, but what you go and do is you go take a picture of it on your iPhone. So the next time you need it, you don't actually have to go next door. You just pull out your phone and look at the list, right? But it still takes you time to open up, get your phone out, look at that list, and that's still not as fast as having it, just right next to you. Okay, and so the other thing is that we're talking about having everything in memory, and that is not a sort of computing world we're in yet. We still all have SSDs and hard drives, whilst the cost is prohibitive to have RAM-only systems. But technologies like this already exist. Intel, for example, have a hard drive you can purchase, which is all based on RAM. It's just all RAM. It's a 200 gig RAM-based hard drive. There's no
Mhm.
hard drive other than that. And it persists the information you store on it when you switch it off. And that's actually the technological challenge. How can you get these memory systems to keep the information they have in them so that they're continuously fast all the time? And so that's sort of the third thing in Hyper's sort of book of tricks. Okay, how do you process information quickly, and how do you get it quickly? Now, the last one, the last key sort of technological uh, achievement for Hyper is the way that it parallelizes tasks. Can never say that phrase properly, so excuse me. It's a bit of a tongue twister. Parallelization. I think I said that right this time. So
Yeah.
parallelization is the concept here. And in Hyper's academic paper, they actually call it something, they call it morsel-driven parallelization. Okay.
Hmm.
And so I'm just going to go straight to analogies here because it's much simpler. Imagine I've got a cake, okay, and I have 4 people, okay.
Yeah.
Now, in modern terms, that's a 4-core CPU. That's a computer processing unit with 4 computer cores, okay. And the most effective way of actually divvying that cake up is to cut it into 4, right? And then I feed each quarter to each person, okay. And the task here is to finish eating the cake, okay. Now, you immediately get problems. For example, what if you're one of those people, Ravi, and you eat cake faster than everyone else? Okay,
Yep.
you're going to finish your cake much sooner, and then in terms of in computing terms, you're going to have nothing to do, whilst me and maybe 2 other people are being polite about eating our cake. You know, we're taking our time, and meanwhile, you've got nothing to do. Okay.
Yep.
The other problem here is that what if a 5th person turns up and I've already cut the cake in 4? It's actually quite hard to just recut the cake into 5 pieces once I've already cut it into 4. I have to go figure out like how much I take off each person's cake,
And then
and
that
then
person gets like a
Yeah,
part of a cake.
yeah,
Yeah. Yeah.
exactly. And if you turn up halfway, people have already eaten cake, and if you're eating cake faster than everyone else, I've got even more complicated maths to do here. And although a computer could do it very quickly, it's still not an efficient way of doing it. Okay,
Hmm.
and so the key challenge here is how do you parallelize a task? Okay. And the way Hyper does it, to simplify it, is it actually cuts the cake into millions of pieces, okay? And it basically
Right.
puts those pieces onto a table. And then it looks to see, well, who's here to eat the cake? Then it just tells everyone, just start eating. Don't worry about which bits you're eating, just start eating the cake. And so everyone's eating cake. And because the bits are so small, if you eat cake faster than everyone else, Ravi, that means you get a bigger share of the cake. There's no sort of equal division based on the number of people in the room. It's just lots of pieces, off you go. And if a 5th person turns up midway, they can also contribute to the task. And if someone has to, go away and do something else, which in computing terms is a processor doing another task,
Hmm.
then that also works. And it essentially means that when everyone finishes eating cake, everyone still finishes at the rough same amount of time, because if you're eating faster, you just eat more cake, and if you eat slower, you just eat less cake. And so this has actually got a wonderful sort of name to it. This guy called Amdahl, who wrote a law. Okay, and when we actually apply it to computers, you start to understand why this is a big challenge. If I take a very simple 32 core Tableau server, okay, and I let's assume we're just sending it one task, and 95% of that task can be parallelized. Okay, and so by that I mean if I'm cutting a cake and the task is to eat the cake, there might be one task which is let me know when the cake is finished. Okay, and that task can't be parallelized because it's essentially one person's responsibility to basically look at the cake and watch the table and let me know when the cake is finished. So if I parallelize a task to about 95%, okay, across 32 cores, what actually ends up happening is that I only get a 40% utilization of my 32 cores. Because of the way the maths works and the way that the parallelization has a drop off, right? It basically means that even with more power, you don't exactly see the benefits. And this is the problem with enterprise hardware and enterprise architecture, is that you don't actually get massively parallelized tasks. And this is how, Hyper sort of combats this by doing this morsel-driven parallelization, it's building resilience against something called skew. And skew is essentially the difference between how processes perceive a task and when they start and when they finish them. Okay, and so
Right.
that's one of the sort of the big benefits. I would give another example, which is very simple. If you have a task that's nearly 100% parallelized, so 99% parallelization, you have 200 cores, you only get a 63 speed improvement, even though you have 200 cores compared to just a single core. And that means you get about 32% utilization. Again, because the drop-off rate
Yep.
is really bad. And so the more cores you shove in there, it doesn't actually mean the more speed you get. And so you're not taking full advantage of the CPU cores that are actually sitting on your computer.
I guess the tricky part is that fact that it's such a big change from moving away from the old system as it was, right?
Yeah,
Like
yeah,
what we have here and what Hyper compared to what Hyper's doing is this is what's revolutionary. I think this is the big crux of it, right? It's
yeah.
this processing speed and the fact it's compounding a query in such a different way,
Mm-hmm.
um, that it's just completely different, and it's hard for a competing technology to do it similar unless it's a new competing technology, right? But I'm talking about the old school
Yeah,
enterprise level,
yeah.
um, enterprise level databases and data warehouses that do this a bit differently.
Exactly. In many ways, you could only really build a database like this if you started building it today, which is what essentially Hyper is. Hyper has been built out of a modern perspective and a modern way of thinking about this. And you might ask, well, why don't all databases do this? And the short answer is that it's a lot of work. If you've built an infrastructure that lots of enterprises rely upon and you suddenly try and change it, that's going to cause bugs. It's going to cause sort of a poor performance for a period of time. So the only way you can get the real benefit is by building something from scratch. And you can obviously understand why that's not in the best interests of some of the existing incumbents, right? You don't want to have to tell your customers, hey, by the way, we're building an entirely new way of working with databases. It might cause problems, but trust me, it's better. Whereas, Tableau customers have traditionally shown that they are interested in new ways of doing things. And at least for now, Tableau can take advantage of the fact that they have a clean sheet and they're building a database from scratch in a modern world compared to the world we lived in 20 years ago.
Yeah, so what I think that Tableau might struggle with here is just the adoption and understanding. Like, I think that a lot of the times when it's being mentioned about Hyper being this innovative process, it's not given its dues in terms of that advantage,
Hmm. Hmm.
because of this thing. Like we're saying it's faster, but we're not. You don't want to explain like everything you just went through about query compilation. Like imagine saying
Yeah.
that in like an elevator pitch. Like if you're speaking to a C-suite guy, he's like, I don't care. Like I don't fundamentally care why it's faster. Is it faster, and am I going to get my results quicker?
And with all due respect to the researchers and the people, the smart minds behind this,
Yeah.
like I'm massively simplifying what I'm saying, and I barely understand it. So, like I read the first page of one of the papers on Hyper, yeah, and it's called Fast Serializable Multi-Version Concurrency Control for Main Memory Database Systems, and I was just like, whoa, what?
MVCC for main memory database systems, of
I was
course.
just like, what does that even mean? Uh, and it and that's the thing. You're talking about incredibly deep level of sort of understanding, and the what everyone takes away from it is it's faster, and it's actually not just that. It's there's a lot more to it, and people just need to spend a bit more time
But
sort of with the
I think
architecture. Yeah.
Yeah, but I think fundamentally it's faster is an easy way of doing it because, as we mentioned, Dr. Thomas Domin is one of what, five people? I don't know. I
It's
don't
like
know what the
a
landscape is.
handful
Yeah,
of researchers that
a
do
handful of
very well.
researchers
Yeah.
that do this and understand it at that level. Which is why, is again, a lot more should be made of the fact that in buying Hyper, they also got one of the leading thinkers in this space.
Hmm.
Um, and it's people like him. It's sort of like when you speak to a developer at Tableau and then they're asking you like, oh, so what are your opinions on what would happen with this thing that we've done? It's like that's like I trust your judgment. It's in a similar way, I trust this guy's judgment that what he's doing is the best and most optimal way, right? Like I'm not
Yeah.
gonna be like, wait a second, I've got a good idea about MVCCC. I don't have that knowledge to do so. Um, But understanding this allows me to be a bit more like, hey, when I'm troubleshooting or I'm trying to understand why something's slow, is it me? No, it could just be the database. It could be the fact that when I'm making this query, it's not as optimized as it could be. Or
Yeah, exactly.
when I'm working with this database and I'm trying to convert it to a hyper, what could be happening is this. It gives me that sort of understanding about why things are happening,
Yeah,
rather than sort of I'm now going to go away and start working on my own hyper database, right?
exactly,
Um,
exactly. And it's actually quite hard to do if you were an incumbent. The
exactly.
funny thing is, all this research is published; it's out there, and there's, in a funny way, Tableau's being very transparent about the innovation here because this is all available to public, and the ideas and the papers are all out there. Other people could very much just read these and think of similar concept, maybe even better concepts.
Exactly, and it's similar to VizQL. Like you can sort of see what VizQL is doing, but you'll be hard pressed to actually replicate and do the exact same thing yourself. Because what people often forget is Tableau's developers and the product launch teams are like 3 versions ahead of what we
Hmm.
see, right? So they're
Hmm.
using it completely, might even be using completely different technology to what we are seeing and using today, the stable version. So I think what you said earlier was right. Like I think the competitive advantage that Tableau have in this case is the fact that every database can't do this. At least the old school ones can't because they'll have to
Yeah.
fundamentally change the core of it. Right? It's
Hmm.
exactly how the processing works that has to be changed.
And
And I guess that go on.
that's the hard thing, steering the cruise liner once it's heading in a certain
Right.
direction is really really hard.
And I think that this leads us really nicely to the now what, which is like, okay, we've now talked about this bit about the hyper and
Hmm.
the innovations and all of these different things about query compilation, LLVM, and all these complex stuff, which basically boils down to it's a bit faster. It's translating a lot quicker,
Yeah,
and it's able to be more flexible, right, in
yeah,
how it approaches a task.
yeah,
Those
pretty
are the three
much.
fundamental things, right? But for me, when we sort of start reading through this and finding out a bit more, is it's the future that's really exciting, right? The fact that
Exactly.
the fact that Tableau's changed from a TD to a .hyper file means that they're able to then say, okay, cool. So we've now got something that's doing things faster in these nanoseconds. How can we use that to leverage and get a marginal increase in how we're approaching like Viz and tooltips, right? How can we
Yeah,
use this to make um, Tableau prep so much better than it already is, right?
exactly. And that's the thing I think that is hard to miss here. Things like Tableau prep are only really possible because of the innovation in Hyper. Charts and tooltips. Again, only really possible because of the integration of Hyper, and it
And
wasn't
even
actually
even then,
until
you've got a bit of lag, right? Like when
yeah, yeah,
there's still that tiny second when you hover over something, and it's like, oh god, let me go fetch that chart, but it's still fetching that chart, doing the filtering, and
yeah,
everything you've set it up to do for you in that moment.
yeah, exactly, exactly. And I think if you're looking at the now what sort of piece, the key thing I'd say here is that what Hyper ends up being, actually, once you take all this into account, is it ends up enabling a type of database that hasn't traditionally existed before. In a typical enterprise context today, you have a transactional system. So this is basically your bread and butter. This is how all businesses work. These are the same kind of systems that if they go down, you can't take transactions on a website, and everything stops. You literally can't do anything else. And then analytics, which is a function of those transactions, is done on a separate layer. So you have maybe an ETL process or workflow that takes the data from your transactional based systems and does it in the analytical systems. And so what you're doing with analytical systems is scanning data. And what
Hmm.
you're doing with transactional systems is actually editing and modifying individual rows. And those two things are so different in terms of the requirements they have. And then you also have what's typically called beyond relational activities. And so these are things like, charting, Hadoop, data mining, things that happen another layer above analytics because they need to happen on a much sort of longer timescales. And it's actually hard to have all these systems in one place because they're all so far removed from the raw data that happens. And so the
And
real
also, and also, this is where you get that latency between,
yeah,
you know,
yeah.
you have the fact you got all your transactional data going into one place.
Hmm.
Then you have to do some ETL on top of that to put it into
Yeah.
your analytics, like data warehouse,
Hmm.
and then you can do your actual analytics, right? Like that's
Exactly.
it's those three-step processes that then add time and computational power and ultimately cost.
Exactly. You have three instances of the same thing basically because of business continuity or risk factors you can't afford to do analytics on the data you should be doing analytics on. And so Hyper tries to sort of solve this by basically offering one place to do this all. And I think that the easiest way to sort of draw people's attention to this is the demo in the Vegas conference, where they had on stage a large amount of weather data from the US. And what they were
Hmm.
doing is they were reading data from a Hyper extract. Number one, it created it really quickly. And even after it created it, what they ended up doing is loading data into the extract without having to refresh the extract. And so this is sort of this idea of being able to do analytics on your transactional data, and then being able to do other bits of sort of analysis on top of that. And if you think of Tableau Prep with technologies such as Python and R being integrated, you
Hmm.
start to be able to do data mining, analytics, and all of this stuff all in one place, in one sort of architecture, as Tableau calls it, the Tableau platform, as it were.
Exactly, and this is the stuff that people often miss out, right? The fact that this technology is enabling so much in the back end, and it's helping the developers at Tableau understand a bit better about, like, hang on. So wait, so if I compile this query in this way rather than the previous way, I'm now getting an X, whatever X improvement.
Yeah,
Why am I not doing it that way? And then you're suddenly unleashed into the wild and able to sort of build out further, right? So
exactly, exactly. Okay. Well,
cool.
that was really dense, wasn't it?
That was very dense. Yeah, that's something to really, like, you it wakes you up in the morning. If the What So What Now What podcast is part of your morning commute, then this will definitely get your brain in gear,
I
and
have
we
I
really
have to say, I
you
feel like
deserve
an
a coffee.
imposter. I feel like an imposter because I've maligned and massively simplified a whole bunch of really advanced concepts throughout the whole entire pod. But it's really interesting. As Ravi said, definitely check out the research pages on the Tableau website. Hyper actually has its own website you can go to. If you just Google Hyper database, you'll find their website, and on there they actually publish all their white papers going all the
Mm.
way back to when they were founded up until today. They have about 50 or 60 no, papers that have now been published that basically touch on everything we've touched on in way more detail. The
If,
other
if if you so wish to find out more, right?
yeah. The other gem is, if you can get hold of it, is the 2016 recording from conference that basically it's called Boom. What is it called? Boom. There goes the database. It's a hyper presentation from the Austin 2016 conference,
Hmm.
and that basically summarizes how hyper works and how it's different to traditional databases. It's about 25 minutes long. It's really good, and there's obviously a Q&A at the end that um, it's funny. Most of the questions and answers from that 2016 sessions have now been answered. So it's a great thing to watch because we're now, 2016. My word, we're
Three
nearly
years
four
on.
years on. Yeah, so 3 years on, nearly four, and obviously we've seen Hyper now, but it also gives us a glimpse of what we haven't seen yet that is going to come. So that'll be really interesting.
Exactly. It's quite fun looking back at, like, even old keynotes and sort of getting that glimpse into, like, hang on a second, they've not talked about that for a while. And it's like, hang on, so maybe it's under wraps and they're going to do a big
Exactly,
reveal.
exactly,
Um,
exactly.
but yeah, no, for me it's been really interesting, mainly because it's given me a lot more topics to talk about and touch on, and a better understanding of exactly what's going on and what's what.
Hmm.
Um, which means I can speak a bit more intelligently about it rather than my soundbite of it. It's just faster. Let me show you this video from Craig Bloodworth where he's comparing a TD extraction to a hyper extraction, how much faster it is. But yeah, it's there's a lot more going on that Tableau can leverage, and it's absolutely something that's quite exciting. in terms of what's possible with it.
So yeah, no, thank you for listening to this episode. You can obviously find us on our website, 3whatspod.com. You can get in touch with us on Twitter, or you can reach out to Ravi or myself on Twitter as well. Do be sure to check out the show notes. We add lots of valuable information in there. Show notes are now available in Apple Podcasts, as well as Overcast or any other sort of podcast sort of app of choice. What do you use, Ravi?
I've actually moved on to Overcast.
Overcast, yeah.
Yeah, because for me the thing that's quite nice about Overcast is the speed controls.
Oh, yeah.
I can 2x, and then also there's the smart speed function which like gets rid of silent periods in a
Yeah,
podcast. So like
yeah.
you don't get the awkward silences when some people are recording. They just get cut out and it speeds up through it. So
Exactly.
you feel like you are learning a bit more in a shorter amount of time.
Yeah, my top recommendations on iOS, it would be Overcast. It's entirely free. If not, Apple Podcasts. And then on Android, I think Pocket Casts or TuneIn Radio, and also Google Podcasts now is a podcast app. So you can use any one of those apps. You can obviously add our feed yourself if you can't find the podcasts on those sites. Just head to our website and add the RSS feed, and you'll be able to listen on any podcast app of choice. Thanks so much for listening. We'll catch you on the next podcast, which will be towards the end of Jan.
Take it easy, folks.